In this session, we'll be understanding the torque speed characteristics of DC motors. We already know that generated voltage EA is equal to K phi omega. I write this as the constant KB. We have found this as phi z and P by 60A. Taking all other as constant, EA, the induced voltage, is KB phi omega. This will also be the back EMF in case of a DC motor. One, and secondly, we have already derived this equation for rotating machines. Torque is equal to 2is RILB, replacing B by in terms of phi, and I here is actually the armature current. Taking all other values as constant, we'll get KT phi IA. This current IA here is nothing but the armature current, and B is equal to I by A, taking A as constant for the machine, and all of the values here as constant. We can see torque is nothing but KT phi A. Now we have two equations. We have the back EMF equation that we need here. That's back EMF is equal to KB phi omega, or in other words, we can say back EMF is proportional to phi and omega, and torque is equal to KT phi A phi IA. In other words, we can say the torque induced torque in a DC motor is proportional to flux as well as the armature current. While having these two as the proportionality constant, this is here known as the back EMF coefficient, and this is known as the torque coefficient. These are known to us now. Going back to the speed equations, the governing equations. Let's start with the shunt and separately excited DC motor. We had the equation Vt is equal to Ea plus Ia Ra for a shunt DC motor. For a shunt DC motor, Vt is equal to Ea plus IaRa, and for a shunt DC generator, it's Vt is equal to Ia plus IRA plus Eb, or what we are referring here as. So instead of using the using Ea, I'll be using here Eb. The back EMF is actually equal to back EMF plus IaRa. Now, substituting the above two equations, from the above equations we have Vt is equal to Kb phi omega plus Ia is tau divided by Kt phi Ra. So from this we have omega will be equal to Vt minus tau Kt phi Ra divided by 1 by Kb times phi. So this is the equation that will relate omega and torque in case of a shunt and a separately excited DC machine. This can be further solved, and we'll get Vt by Kb phi minus tau minus, instead of writing tau in the numerator, I'll write minus Ia minus Ra Kt Kb phi square times tau. So omega is Vt by Kb phi minus Ra Kt Kb phi square times tau. Now we have to plot this. We can see as the induced torque in the motor will increase. So initially, if torque induced is 0 at tau equal to 0, omega kb phi. It will have a finite value. As tau increases, omega will simply decrease. So will be a linear decrease in this, uh, depending upon the values of kb and kt here, while assuming that the flux is constant. So this is the speed torque characteristics of a DC shunt generator, DC shunt motor, and a separately excited DC motor. They will have somewhat nearly similar type of. Mm. Now, what will be the effect of armature reaction here? Will be opposed to that of a generator. With an armature reaction, this will be the torque speed characteristic. So this is without armature reaction. This is with armature reaction. Note here that phi is in the denominator. So as phi decreases, uh, omega will increase. Uh, Initially, the effect of phi and phi square will be almost negligible, but as it increases, this effect of phi square will dominate over phi, and since it will net over decrease the effect of this negative term, that means our speed will increase. So for lower values of phi, phi and phi square will be almost similar. There will not be much effect, but as phi keeps on decreasing further, for higher decreases, there will be a larger, there will be a dominating effect of phi square over phi. So eventually the speed will increase with the armature reaction. Now for a series DC motor, the equation that we had derived was for a motoring mode, Vt is Ea plus Ia Ra plus Rf. Vt is equal to Ea plus Ia Ra plus Rf. Now again we know that Ea is nothing but K B phi omega. Ea here is the back EMF actually, and Ia is tau divided by Kt phi Ra plus Rf, which implies omega will be Vt divided by Kb phi plus uh, minus rather tau divided by Kt phi into Kb phi. That means this is Kb Kt phi square Ra plus Rf. So the only difference here is that we have Ra plus Rf into tau rather than simply Ra times tau. Now, as opposed to that of a case of a DC generator here, we do not need the field winding uh, to produce the we do not need the field winding to produce Vt. Vt will already be established in this circuit. Vt we are actually providing to the Vt is the applied voltage in case of a DC motor. So in case of a DC series motor, so we are saying in case of a DC motor that this will again be a linear fall. The difference here will be that the starting torque will be much larger as compared to that of uh, the shunt DC motor, and the fall will be more as we have additional resistance and neglecting the effect of additionally we have RF in association with RA that will make the negative component more, so there will be a larger amount of fall. So if this was the torque speed characteristics of a shunt DC motor, these are the characteristics of a series DC motor. Now in case of a compound DC motor, we will find out a similar type of equation. The difference will be that in case of a shunt DC motor, the torque speed characteristics will lie somewhere in between the series and shunt DC motor. So these are the torque speed characteristics of shunt series and DC motors. In the next session, we'll discuss the applications of DC motors and also the speed control methods employed in DC motors.